Nice.
Okay.
So now you see, yeah, it looks like a presentation of your talk, and the floor is yours.
So you can also see my marker.
Yeah,
okay,
we can
thank
see
you very much.
Yeah, everything is fine.
Yeah.
Yeah.
Yeah, thank you very much, Lena, for giving me a chance to give a talk in this workshop. So this is based on joint work with Kai-Xiong Wang, Yuefeng Yang, and Wenin Zhu. Okay, so the topic of my talk is about weakly distance regular circulants. So somehow it is related to distance regular graph, but it is not quite distance regular graph, but rather they are digraphs, not the undirected graph, but the directed graphs. Okay, so I guess almost everyone knows the definition of distance regular graph, but just for the purpose of comparison, let me start with the definition of distance regular graph. So for connected graph gamma and its vertices, we denote by delta xy the path length distance in gamma. So that is the length of the shortest path from a vertex x to vertex y. And the diameter of gamma is the largest possible value of this distance. And this is finite because the graph is connected. Now, the definition of distance regular graph, not the standard definition, but in the spirit of association scheme, is like this. So you take x and y at distance k, so you pick this, and count the number of z, which is distance I from x and distance j from y. And this number does not depend on xy, but it depends only on k. Of course, it may depend on I and j. And that's the definition of distance regularity. So there's a book about this topic or this subject written by Brouwer, Cohen, Neumeyer, published in '89. So this is a very standard topic in algebraic graph theory. And my talk today is about the directed analog of distance regular graphs. So if you allow directed edges or digraphs, then the definition needs to be modified. Well, there are several variants of directed analog of distance regular graphs. First of all, because this distance regular graphs are essentially the same as p-polynomial association scheme. So perhaps the most natural analog I can think of is in terms of p-polynomial association scheme, so that the directed analog is also p-polynomial, although it is not symmetric. So in this sense, Damerel first defined this concept, and Liebler and Mena gave an infinite family of examples, although it is small in terms of diameter. And then Leonard and Nomura show that in fact the diameter is absolutely bounded. So you cannot hope to have a rich theory like in the undirected case. So there are three more variants. So the second variant is the directed strongly irregular graphs introduced by Art Duval. But this is not the analog of a distance regular graph, but the analog of a strongly irregular graph. Although this has been investigated by many researchers. And there's a third variant is introduced by Komela, Theo, Gimbart, Michiana. They call it weakly distance regular graph. and they use the number of walks. So it is analog of a distance regular graph in the sense of metrics theory. So, but this has not been studied very much as far as I know. And the last variant is the one we used, although it carries the same name as the other variant, but the definitions are actually inequivalent. So this was introduced by Kaishu Wang and Hiroshi Suzuki in 2003, also called weakly distance regular diagrams. So let me give a definition of this last analog of distance regular graph. This is almost the same as distance regular graph if you are familiar with the association scheme. But the concept of distance had to be modified because, well, in a digraph, one cannot talk about distance between two vertices, because if you decide to define distance in terms of the length of the shortest path, well, the path had to be directed. So we have to assume the graph is strongly connected, that meaning that any pair of vertices can be connected by a directed path. So then we can consider the minimum length of such a path and call it distance, but this is not the proper distance, or it doesn't satisfy the axiom of metric because it is not necessarily symmetric. Nevertheless, we could call the largest value of this kind of distance as diameter. And the main difference from the undirected case is that this two variable function is not symmetric. Well, if it is not symmetric, then it means that the pair of vertices xy determines two possibly distinct values that we call two-way distance. So if you take two vertices x and y, the distance, that is the length of the shortest directed path from x to y, which I denote by I, this I may be different from the distance measured in the other direction, say I prime, that is the length of the shortest directed path from y to x. So any pair of vertices determine two integers, distance from x to y and distance from y to x. So these two integers take value from 0 to d. D is the largest possible value. So we consider the collection of all pairs of this kind of distance and denote by the tilde delta of gamma. So this is a set of pairs of integers from 0 to d. Of course, the 0, 0 is certainly in this set, and one of the two coordinates is 0, then the other is necessarily 0, because that means that comes from x equal y. And but other than that, you don't know, you can't say much about this set. And this is going to be the set indexing the set of relations of our association scheme, or this is you may think of the set of colors which color arcs of complete digraph. Okay, so if you take ij, a pair of integers in this tilde delta, tilde d of gamma, then you collect all pairs of vertices xy such that this two-way distance equals ij. And so this is kind of relations on the set of vertices, and I denote by rij. And we say the graph gamma is weakly distance regular if this collection of relations is an association scheme. Well, I don't give a definition of association scheme, but the equivalent characterization is this one. Well, so it is essentially the extension of the definition of distance regular graph you have seen a few slides earlier, that you take two vertices x and y, and then count the number of vertices z, which have in specific relation with x and y. So, to specify the relation, we need to specify two integers, I prime, jj prime, and kk prime, to specify the color of the arc. But other than that, the definition is quite parallel to the ordinary distance regular graphs. That we require that this number of vertices z depends only on the pair kk prime, but not on the choices kx and y. So this generalizes the definition of distance regular graph, because if gamma turns out to be an undirected graph, then this two-way distance is just symmetric. So this pair consists only of those which I is equal to j, or I is equal to I prime. And then in this case, the axiom reduced to the definition of distance regularity. So for the rest of the talk, I will exclude the undirected case. So, well, formally speaking, if you define weakly distance regular graph in this manner, then it includes distance regular graph by definition. But let's put them aside and let's focus on the directed graph, which is not undirected. Okay, here's an example. This is a Cayley graph on cyclic group of order 4 with connection set 1, 2. So this is not the Cayley graph, but the Cayley digraph. So here's a picture that we join two vertices x and y if y is 1 greater than x or 2 greater than x. So there are two kinds of arcs, that is the difference 1 or difference 2. So difference 1 constitute a 4 cycle, and difference 2 are just diagonals. And the only other relation is that the difference -1, which is the opposite of the arc going in the other direction. And we don't regard that as an arc, but we only regard difference 1 and 2 as an arc, because that's how the Cayley digraph is defined. And so there are essentially two types of arcs. So the first kind of arc, which is like this one, this arc consists of xy belonging to this set. This 2 means that if you try to go back, then it will take 2 steps. Let's see why. So if you have this arc, if you try to go back, then let's see how okay, 1, 2. So there are 2 steps needed. You cannot go back directly because there is no opposite arc. On the other hand, this arc has its opposite. So this is why we write 1, 1. So two-way distance is the pair 1, 1 for this cell. So this is one of the perhaps the smallest non-trivial example of a weakly distance regular digraph. The requirement is that this set of four relations is association scheme, but it is rather obvious. In fact, this is so-called group association scheme of the cyclic group of order 4. Okay. Next example is a little bit more complicated, but we consider the lexicographic product. So lexicographic product, here I use K3 and C4. C4 is a directed cycle of length 4, and K3 outside C4 means you make 3 copies of C4, which is depicted here. So there are 3 copies. And the lexicographic product means that you make arcs originally in C4. So we have arcs like this, and those are this arc, and also make more arcs coming from K3. That is, for example, from this vertex, I add more edges. The first coordinate corresponds to positions. So as long as they are different, then I draw arc like this, and this is an undirected arc. So arc in both directions. Okay. So this is the lexicographic product. Again, there are 2 types of arcs. This is an arc, and this is an arc because this first index is 1. And for this first type of arc, it takes 2 steps, for example, like this, to go back. So this is why number 2 appear here. And the undirected arc always has 1, 1 as subscript. And again, this is an example of a weakly distance regular graph having 2 types of arcs, one of which is undirected. And it's easy to generalize this to Kn of C4. Instead of K3, we could consider Kn. Just n copies of C4. Okay, another doubly regular tournaments. This is also examples of Paley tournaments. We have seen Paley graph on the first day of the conference, but the Paley tournaments are directed graphs, not the undirected Paley graph. So difference is that we need to take prime power q, which is congruent to -1 modulo 4, not 1 modulo 4, so that the set of squares does not contain -1. So here's example on 7 vertices. So it's very known that the such a tournament is a association scheme of rank 3, non-symmetric. Here you see arcs everywhere. So any pair of vertices is joined by an arc, but the direction is uniquely determined. So there are no undirected arc. So there is only one type of arc. So the set of arcs is this R1, 2. For example, if you want to try to go back from this vertex to that vertex. I need to find, maybe let's try to find the easier one. So so you can go this way by one step, and if you try to go back, then you need to take this. So this is why R12 and all Peking tournaments have this property, or more generally, doubly regular tournaments have this property. And so the set of arc is R12, and its complementary set, or the opposite or transpose is the other pairs of vertices. And this is a example weakly distance regular diagram. Okay, here's a more example, direct product of graphs, well, rather digraph. So if you have two digraphs, gamma and delta, and consider the direct product of their vertex sets, and arc sets are just arcs, x, y, and x prime, y prime, when x is joined by arc to x prime, y is joined by y prime to arc, by an arc in delta. So for example, if gamma, well, maybe this is not proper. No. It's a little bit conflict of notation. So this gamma shouldn't be this gamma. So I denote this, the second gamma, the result of the direct product. So the C3 times K4, so you have 12 vertices, and arcs are C3. The C3 means a cycle of length 3, so we have like this cycle. And K4, I have K4, which is like this. And this, for the neighbor of this vertex consists only of these 3 elements, not this one. This one is excluded because this vertex and this vertex are not joined by K4. They represent the same vertex in K4 that violates the second condition. So I didn't depict all the edges, but I only draw edges originating from this vertex, and there are 3 edges. And similarly, if you draw edges originating from this vertex, then there are 3. So this is a vertex digraph without degree 3. And it turns out that this is a weakly distance regular digraph, and the set of two-way distances is like this. So I didn't define the valency, but the valency of digraph is just the out degree of the digraph. So in terms of the notation for the two-way distance, the tilde, then we consider the out neighbors. Out neighbors have two-way distance 1 in its first component, but the second component are arbitrary. So this is the set of out neighbors, and because of the axiom of association scheme, this is independent of the choice of the vertex x, and so that is called the valency of the digraph, or if we assume gamma is weakly distance regular, then this is independent, and we call it valency. For example, this Peking tournament on 7 vertices, well, it had out degree 3, so it has valency 3. There's a similar KD digraph not the Peking digraph, is this one on 13 vertices. Again, of valency 3. Here, I don't consider the set of squares, but I consider the set of fourth powers. The set of fourth power consists of 1, 3, 9. And so I take this as a connection set for this KD digraph, and it turns out that this is a weakly distance regular digraph of valency 3. Well, if you are familiar with the theory of association scheme, then you can recognize this as a cyclotomic association scheme on this finite field F13. Well, this is nothing but the cyclic group of order 13. But I need a multiplicative structure to describe this connection set. Okay, so another concept I need is the girth. Well, this can be described easily in terms of the two-way distance. The girth of the digraph is the length of the shortest cycle or shortest directed cycle of gamma. So if you think of this girth in terms of two-way distance, then it is the smallest value 1 plus I, because the two-way distance between these two vertices is 1 comma I, and that makes directed cycle of length 1 plus I. So the smallest possible I gives smallest possible G, and that is the girth. The girth could be 2. This is a little bit different from the situation of undirected case. In undirected case, we don't allow girth to be 2, but here we have we treat a directed graph. So it may happen that you have arcs in both directions, like this. In this case, we say gamma has girth 2. We have seen that this situation occurs, for example, in the lexicographic product. So we don't exclude such undirected arcs in the digraph. So our digraph could be a mixture of proper digraph and undirected graph. Both kind of edges could exist. So roughly speaking, there are many different kinds of weakly distance regular digraph, but it can be classified into subclasses. First, those with undirected edges, that is, having girth 2. Well, because we exclude ordinary distance regular graphs, so our graph must have a arc, and our graph must have a directed arcs. So girth 2 means you not only have undirected edges, but also directed arcs. So that's one possibility. The second possibility is that gamma has only one type of arc, hence the girth cannot be 2. We don't allow undirected arc. And the third possibility, the girth is greater than or equal to 3, but the gamma may have more than one type of arcs. For example, you could have this one I, but there may be some other arc which have different distance, backward distance. That's the third case. So there are classification theorems for valency 3. Well, like in the distance regular graphs, well, the distance regular graphs of valency 3 have been classified many years ago. And so the weakly distance regular digraph of valency 3, well, it took a lot of effort to do that, but they classified still under the assumption of commutativity. Commutativity means that the corresponding association scheme appearing in the definition of weakly distance regular digraph is commutative. Under this assumption, the weakly distance regular digraph have been classified for Valency 3 in 3 or 4 cases. When the girth is 2 by Kaishu Wang, and when girth is 3, commutative, and gamma has 2 types of arc by Yang, Lu, and Wang, and again commutative, but only 1 type of arcs and by the same author. And well, Suzuki also classified gamma has 3 types of arcs. Well, it has valency 3, so you can't have more than 3 types of arcs. So essentially, this is what is known about the smallest valency. Well, in fact, the valency 2 predates these work, but it's already non-trivial to classify the weakly distance regular digraph of valency 2, unlike the distance regular graph of valency 2, just cycle. Now, the commutativity amounts to the following property. So suppose you have vertices here, that the arc of type ij, arc of type I prime, j prime. Commutativity means that there exists vertex here, which whose relation with respect to these 2 vertices are switched from this one. In fact, the number of such vertices is also the same as the number of such vertices. So this is what the commutativity means, and this property is used in classifying these weakly distance regular digraphs. Yeah. So in this talk, we try to investigate circulant weakly distance regular digraphs. We have seen already this circulants. That is, for example, if you have a Paley tournaments on prime number of vertices, then it is certainly a Cayley graph or a cyclic group. So it is a circulant graph. And Paley tournaments, as well as this 4th power Cayley digraph, is a circulant weakly distance regular digraph. In this second example, its distance relations define, in fact, the cyclotomic association scheme. So this is this is a 4-class scheme. The set of relations are indexed by the 2-way distance 1, 2, and its opposite, and so 2, 3, 3, 2. No other 2-way distance appear other than this obvious 0, 0. And in terms of connection set, the arcs have connection set 1, 3, 9, and the opposite arc, and the distance 2, but not opposite one, are 2, 5, 6, and its opposite. It turns out they are known as the cyclotomic classes, or they are residue class of the subgroup of index 4. Well, for undirected case, there are classification of circulants. So strongly irregular graph, which are circulants, these were classified many years ago. Bridges, Mena, and Hughes, Van Lent, Wilson, and Marr already in 70s, 80s. And there aren't so many such strongly regular graphs, apart from trivial ones, that is complete graph or complete bipartite graph. The Paley graphs on prime number vertices are the only such examples. And then after that, Miklavich and Potocnik in 2003 classified distance regular graphs, which are circulants. Well, distance regular graph contain strongly regular graph. It's a wider class, but essentially there are no non-trivial example arises. There's one graph called cocktail party graph, but that's the only addition to the strongly regular example. So in this talk, we aim to present our result on classification of weakly distance regular digraphs, which are circular. And we have tournaments, Paley tournaments on prime number of vertices. And also this cyclotomic scheme on 13 vertices of index 4. That was an example. But what else do we have? Well, we have seen some example, but I didn't mention whether they are circulant or not. So here is our classification theorem. So a digraph gamma is weakly distance regular circulant. Circulant means there's a regular cyclic group of automorphism of one type of arcs. So I need to assume that it has only one type of arcs. If and only if gamma is isomorphic to one of the following digraphs. So first, the lexicographic product of cycle of length L and complement of complete graph on M vertices. In other words, this is also known as a cyclic extension. And similarly for the Paley tournament extended by a cyclic. And the third one is a direct product of a cyclic, 3 cycle. We have seen this one. And that last one is the sporadic one, the cyclotomic scheme on 13 vertices, but then you can also cyclic extension. You extend the cyclic by this cyclotomic scheme is still on weakly distance regular circular. And that's the all examples. So the proof of the theorem relies on the structure theorem S rings over cyclic groups, mostly developed by Sergei Yevdokimov, Ilya Ponomarenko, Misha Muzichuk, and Istvan Kovac. Yeah, this is why we consider the circulant graph, and also the weakly distance regular means that it is in some sense related to association scheme. The association scheme with the regular automorphisms group are nothing but S rings, which I'm going to introduce. But before introducing, let me mention examples again. So from the definition of weakly distance regular digraph, we know we get association scheme that is a coloring of arcs of a set of vertices indexed by two-way distances. So basically the weakly distance regularity requires that this partition satisfies certain regularity condition. If gamma is circular, then we may identify the set of vertices with the cyclic group Zn, and then this partition of the set of arcs gives rise to a partition of the set of vertices, which is the set of group elements Zn by considering the neighbors, out neighbors of the vertex 0, which is the identity element of the cyclic group. So you look at the 0 element and consider the neighbors of the edges of color ij. And if you let ij run through all possible colors, then you get a partition of the cyclic group Zn. And for example, we have seen this this cyclotomic scheme. The fourth powers is a subgroup 139, and the two-way distance partitions the neighbors of 0. That is that gives connection set of each KD digraphs. Okay, so in this way, if you have a weakly distance regular circulant, then you get the partition of a cyclic group, and one of the parts is 0, and the other parts correspond to the colors or two-way distances. So S ring is defined in the following manner. So we consider a partition of a finite group, and if you have a subset X, then consider X bar, that is the formal sum of elements in X in the group ring over group ring of G over the integers. And if a partition S satisfies the following three conditions, then we call A an S ring. So the first condition is that this singleton set of identity element is in S, and the second condition says that it is essentially closed under taking inverse of each element, and the third condition is that it is the linear span of this X bar, where X runs through this partition S, is a subring of the group ring. And this translates to the regularity condition of association scheme. So when we have a weakly distance regular graph, then the partition obtained by out neighbor of 0 give a S ring. So this is how we got the S ring from the weakly distance regular circulant on 13 vertices. I said that these partitions, except 0, are cosets of the subgroup of index 4, 139. Well, this is a multiplicative subgroup, but you may think of this subgroup acting on F13, additive group, as a group of automorphism. Not the full group of automorphism, but the subgroup of automorphism. And these 4 cosets are orbits of this group of automorphism. You can generalize this construction that if you take a subgroup of automorphism of a finite group, and then it gives a orbit partition, and such an orbit partition automatically defines a S ring. So one could call this an orbit S ring. And this concept is needed in the following, in the slides to come. So this is essentially what I said already, that when we have a weakly distance regular digraph, which is a circulant, in general, weakly distance regular digraph gives an association scheme, but from the association scheme, we obtain an S ring, because association scheme can be used to define the set of out neighbors of identity element, and it gives a partition, and the property of an association scheme implies that it is indeed an S ring. So classifying weakly distance regular circulant amounts to classifying certain S-ring over cyclic groups. S-ring over cyclic groups in general have been investigated by, for example, Elia. So the main results on structure of S-ring over cyclic group is like this. So suppose you have a S-ring over cyclic group Zn, and then there is a subgroup L such that if we denote by pi the linear extension of the canonical surjection from Zn to its quotient by L, that gives rise to a group ring homomorphism, and the image of the S-ring A, well, it makes sense to consider the image because S-ring A is a subring of the group ring. And A prime is also a subring of the image, which is also a group ring over the quotient group. And it turns out this is a S-ring over the quotient. And this quotient is decomposed into tensor product of S-ring. Well, I don't have time to define tensor product, but it is more or less same as the direct product of graphs. I mentioned the direct product graph. So you collect all possible direct product, then you get this direct product, not the direct product, but somehow for some reason we call it tensor product of S-ring. Moreover, one of the factor of this tensor product is 0 is an orbit S-ring that I mentioned as an example, and all the rest are pretty simple. They are S-ring of rank 2. The rank 2 means that the partition is trivial in the sense that you have a single partition of the identity, and the rest all consists another part. So the partition into 2 parts. So this is the structure theorem obtained by results of these authors. And so we mean to apply this theorem for the S-ring obtained from a weakly distance regular circulant. So this theorem gives information on how our graph look like, or how a digraph gamma look like. It turns out corresponding to this partition, we have a direct product of our graph extended by a cyclic extension. So, well, here I wrote we see, but it involves a lot of work. So here I am omitting a lot of details, but after doing hard work, this theorem translates to the result on a weakly distance regular circulant, and it must be of this form. But not all such digraphs are weakly distance regular circulant. In fact, our classification theorem doesn't list graph of this general form, but rather some special cases. So here is the sketch of the proof. After showing that gamma is of certain forms, we further restrict gamma to a special type. Those 4 are the results I stated in our theorem. So how do these 4 arise? If gamma has girth greater than 3, then the first case occurs. And now suppose gamma has girth 3, then in general, we have, due to the structure theorem of S-ring, we have this general shape, and gamma 0 is an orbit S-ring. Now, because of the orbit S ring of, in fact, a cyclic group, then we can say a lot about the orbit S ring. Well, orbit S ring is much more restrictive than general S ring, so we can actually determine possible orbit S ring and hence gamma 0. So there are not so many possibilities for gamma 0. Those are the one we have seen already, the cycle of length 3 and Paley tournament, and the other one on 13 vertices. And once we determine gamma 0, then this extra factor almost vanish, and this M also sometimes vanish, and we get these 3 possibilities. Well, this is very, very rough sketch, and details are completely omitted. But I plan to finish writing this paper, hopefully within this year. Okay, so that's the end. Thank you very much for your attention.
Thank you so much for this talk. Questions to Akihiro? Well, there is a question from Antonina Hramova. So can you say something by yourself, Antonina? Well, okay, there is a question from Antonina Hramova. Thank you for the talk. Do you know if there are any results on classification of circulants for Weakly distance regular graphs using the other you mentioned by Camelius Fuel et al.?
Okay, the question is if there are any results on classification of circulants of Weakly distance regular digraph using the other definition. Other definition? No, I don't know. Somehow I cannot share it.
Okay, fair enough. Thank you for answering this question. Any other questions? So actually, how huge is the proof? I mean,
the main part also contains about 10 pages. So I omitted the details in the last slide, and also next to the last slide, and that argument takes about 10 pages.
For all cases?
Yeah,
because
to
cases,
cover all
right?
Yeah. Some cases are rather easy. For example, the Girth greater than 3, and it's not difficult.
So what is the most complicated case?
The most complicated case, I think, well, the other 3 cases are equally complicated.
I see. Okay, any other questions? Well, if not, then let us thank Akihiro for this nice talk and very interesting results. Good luck with writing the manuscript.
Thank you very much.
Thank you very much.
Thank you very much.